My name is Ferdinand Anak Rengga with metric number 58614. Today, I would like to present my FYP. The title of my FYP is the investigation on the effect of dielectric constant toward resonant frequency by using microstrip patch antenna. The outline of this presentation is as shown. Picture above shows an example of a food analyzer. As we know, not all people are afford to buy a food analyzer, which might cost more than 6,000. Not only that, the weight of a food analyzer is approximately 100 kg or more. Therefore, it's quite impossible to have the food analyzer, which we can say will occupy a lot of space. Compared to microstrip patch antenna, it is less costly and wireless, especially small end product detector which contain a microstrip patch antenna. Lastly, the microstrip patch antenna can be produced in a mass production compared to food analyzer, which is very limited. Adding fluorescent material will lead the dielectric constant of a pure solution to be changed. When the dielectric constant change, its properties will be changed also, consequently affect the reflection coefficient of S11 of the solution. In this research, instead of observing the changing of reflection coefficient, I want to use the antenna to see how the fluorescent material affect the related signal, which known as resonant frequency. Therefore, I want to test the performance of the microstrip patch antenna as a detector to detect changes in resonant frequency. In the previous research, they are also using microstrip patch antenna as a detector for salinity and solute detection, but there are few differences set up compared to my research. Coaxial probe feeding technique is used as signal supply in the research. Not only that, they are also using taconic Wi-Fi as the substrate for the antenna. The width and length of the substrate is 64.8mm and 39.2mm for the width and length of the patch. I will explain more further on the differences between previous research and my research in other slide. My first objective is to design a microstrip patch antenna that working at ISM band. After successful design, simulate and fabricate the antenna, I will use the antenna to fulfill the second objective, which is to analyze the changes of dielectric properties and resonant frequency of different concentration of salt and sugar. Lastly, to investigate the relation of dielectric properties and resonant frequency of different concentration of salt and sugar. For scope of research, the main objective of this research is to use the microstrip patch antenna for investigation of relation between the electric properties and resonant frequency of different concentration of salt and sugar. The microstrip patch antenna that use FR4 or flame retardant type 4 as substrate was initially designed and simulated using CST Microwave Studio. Then, 6 samples of different concentration of salt and sugar is prepared. As already been mentioned, the impurities of salt and sugar will alter the dielectric constant of a pure solution, thus change its dielectric properties. Observation is made upon the changes of dielectric properties and resonant frequency for each sample. Therefore, vector network analyzer or VNA will be used to measure the reflection coefficient and shifting of the resonant frequency. Last but not least, the graph that compare the reflection coefficient and resonant frequency for both salt and sugar solution will be presented to analyze the relation. Two diagrams above shows the front view and back view of the fabricated antenna. Now, I will explain the differences between the previous research and my research. For my research, I am using microstrip line feed to supply the signal from the VNA to the microstrip patch antenna through coaxial cable. The feeding technique is very easy compared to coaxial probe feed, whereby my technique only requires some calculation to determine the configuration. On the other hand, the previous research required to find the exact feed point to obtain the minimum impedance mismatch through simulation. Next, although the previous research using taconic Wi-Fi as substrate, which is performed at high performance and a communicator, but the availability is low compared to FR4. When comparing to the size of the antenna, my antenna is slightly smaller compared to previous research, which is more suitable for small end product. Sometimes you need to go. My flow chart is designed as follows. Various steps is required to complete my research. Initially, my targeted frequency is 2.45 kHz. Unfortunately, due to some unwanted accident during the fabrication process that will be presented in the slide, my new resonant frequency is 2.60 GHz. The table shows the overall process of FYP1 and FYP2. The Gantt chart is very important to guide me in completing my research. In my research, microstrip patch antenna, VNA, and container with different concentration of salt and sugar is required. Above shows how my setup will be. The fabricated antenna will be connected to the VNA through sub-miniature version A or SMA port. Then the antenna will be placed in a container which contains the solution of salt and sugar of different concentration. The resonant frequency will appear on the VNA screen. This slide shows the front, back and side view of the setup for the microstrip patch antenna in the container. The graph shows the result from the simulation using CST Microwave Studio. 2.45 GHz is the initial targeted frequency with S11 of -14.96 dB. Again, due to unwanted accident that occurred during the fabrication process, the new resonant frequency is 2.60 GHz with S11 of -13.3 dB. This measurement is made during the container is empty. The graph shows the resonant frequency and reflection coefficient of a pure solution. There is a small shifting to the right hand of the original radiated frequency with reflection coefficient of -16.8 dB. Now I will show the result of 10 from the VNA for salt solution. For the testing and measurement, 20 gram, 30 gram and 40 gram of salt is used. As we can see from the graph, different concentration produce different value of resonant frequency and reflection coefficient. As for the shifting, the resonant frequency is shifted to the right along with the increment of salt. For reflection coefficient, the value is also increasing. The exact amount of 20 gram, 30 gram and 40 gram of sugar is used. The shifting of the resonant frequency is mostly to the right from the original radiated frequency, which is 2.60 GHz. The reflection coefficient also increased along with the increment of concentration. Both resonant frequency and reflection coefficient are different from each other. Table 1 shows the summary of results for both salt and sugar solution in terms of resonant frequency and reflection coefficient. Table 2 shows the parameter comparison between simulation and fabricated antenna. As already been mentioned, my targeted frequency of 2.45 GHz is not achieved. Instead, my antenna radiated at 2.60 GHz. As you can see, there are slightly difference in almost all parameters. The main reason is because almost all process of fabrication is handled by humans, which is the staff. Therefore, the probability of getting human error is high. Next, during the designation using Proteus, the size of the antenna is not suitable or reaching the maximum requirement size. Therefore, the staff need to design the antenna more bigger in Proteus. Therefore, I need to cut the excessive part manually using PCB cutter. Other than that, the design of my antenna that is being printed on a transparent paper for UV exposure is not accordingly to the simulation measurement, as the design is initially being transferred to AutoCAD software. Moving to result of salt and sugar concentration, as we can see from the previous slide, the shifting for both solution is mostly to the right hand. The distance from the original resonant frequency to the shifted resonant frequency indicates the total concentration in the pure solution. The further the resonant frequency is shifted, the higher the concentration. This is because the resonant frequency and reflection coefficient are affecting with each other. When the antenna is exposed to a solution that has a concentration of salt and sugar which is different with the dielectric properties of free space, the minimum peak of reflection coefficient for 2.60 GHz will be shifted to another value of resonant frequency accordingly to the new value of the reflection coefficient. This is because the signal that is transmitted and received is being blocked by the resonant resistance from the salt and sugar solution. Therefore, the resonant frequency need to shift to another value which allow the signal to be received during the radiation. In conclusion, a microstrip patch antenna that radiated at 2.60 GHz is successfully fabricated. The shifting of resonant frequency is occurred due to salt and sugar that change the properties of the pure solution. The higher the concentration, the more further the resonant frequency will be shifted. This applies for both solutions. The resonant frequency is shifted because low power signal is radiated and received due to signal blocked by the solution. Increasing the concentration of salt and sugar will increase the level of resonant resistance, thus decrease the efficiency of radiation. As for reflection coefficient, the higher the reflection coefficient, the higher the resonance resistance will be. That's all from me. I hope my presentation is clear regarding my wishes. If there is any question, don't hesitate to contact me. Thank you.